In this series of videos, we're going to go over some result regarding angles related to a circle on Euclidean plane. The results here are not only interesting but also quite useful when we are studying problems for Euclidean geometry. And we will begin with reviewing a few terms. Since those terms are supposed to be familiar from your experience in elementary geometry, so we will go over this part relatively quickly. We will begin with the following terms. A semicircle is the part of the circle which is on one of the half plane obtained by considering a diameter in union with those 2 points on the diameter. So, which means a semicircle is precisely a half of a circle. And on the other hand, a minor arc is supposed to be the parts of the circle which is contained in the interior of a central angle. So recall that a central angle is an angle with the vertex at the center of the circle, and with those two edges touching the circle. So just like the semicircle, the minor arc is supposed to be this part, which is in the interior of the central angle in union with those two endpoints, A and B. In contrary, the major arc of a circle is supposed to be the part of the circle that is in the exterior of a central angle in union with those two endpoints, A and B. So we have the semicircle, the minor arc, and the major arc over here. On the other hand, well, we know that given 2 points, 2 distinct points on the circle, well, you could talk about either the minor arc or the major arc. So there is some kind of ambiguity in terms of which parts of the arc those two endpoints are referring to. Therefore, we usually would use the following notation specifically when we are trying to talk about this arc over there. We would just randomly pick a point on this arc distinct from point A and point B and denote this arc as the arc ACB. So by picking a point on the arc, the ambiguity that we have mentioned would be eliminated, and it's clear which arc we are talking about. Now, with the idea of arc at hand, what we're going to do is going to be looking at the measure of arc as we are looking at on the screen here. So you see, since we have been following the convention of SMSG, namely the School Mathematics Study Group, therefore, in this convention, the measure of an angle is a number in between 0 and 180 degree. But I mean, you may remember from your elementary geometry class that usually an arc on a circle could be measured all the way from 0 to like 360 degree, the entire circle. Therefore, when we are going to incorporate the measure of an arc on a circle into our system of SMSG, we will have to break the definition of the measure of an arc into a couple different cases. And in general, we're going to be considering the following 3 cases. For instance, when we're talking about a semicircle, then we will simply define the measure of the arc to be 180 degrees, pretty much matching up our previous experience with elementary geometry. On the other hand, if we're talking about a minor arc, then we will be expecting the measure of the minor arc to be less than 180 degrees. Specifically, by definition, now here is the definition of the measure of arc really coming into play. And this definition is like how arc of a circle is related to some angles. For instance, in this case, is the central angle. So, but anyways, so let's get back to the definition of the measure of the arc. Well, specifically, when we're looking at minor arc, then the measure of the arc is going to be defined as the measure of the central angle with A and B as the endpoints of the arc, and O is the vertex of the angle, right? And lastly, if we're looking at a major arc, for instance, in this case, the arc ACB is a major arc. And now when that is the case, the measure of this major arc is going to be defined as 360 degrees minus the measure of the central angle with A and B sitting on those two edges of this angle. So that would be our definition of the measure of arc. Now, to familiarize ourselves with the terminology, the notions, um, and the relations that we have just reviewed, we're going to work on the following theorem as a practice on working with all these notions that we have just introduced. So the theorem says, if two chords of a circle are congruent, then their corresponding minor arcs have the same measure. So for instance, let's look at the figure down there, which is elucidating the theorem. Now in particular, in this figure down there, we are assuming that the chord AB and the chord CD are congruent to each other. And what we want to show is that those two minor arcs, APB and DQC or CQD, are of the same measure. Well, but let's try to think about what we are really trying to prove. Well, recall that by definition, the measure of the arc is simply given, and in this case for the minor arc, is simply given by the measure of the central angle. So indeed, what we really want to prove here is the measure of the central angle BOA and the measure of the central angle COD are the same. Well, but if the measure of two angles are the same, then those two angles are going to be congruent to each other. Hence, what we are supposed to prove is, in fact, the congruence between those two angles, BOA and COD. So talking about proving the congruence of two angles, I guess it's quite natural to think about demonstrating some congruence of triangles, right? So what we're going to do is going to establish the congruence of some triangles. Specifically, as you may have already observed, the natural choice to consider are the triangle BOA and the triangle COD. And it's in fact quite straightforward to show the congruence between those two triangles. And the reason being is simply because we observe that the line segments BO, AO, CO, and DO are all radii of the circle in question. Hence, we merely observe that all of them are congruent to each other, right? Now, by the side congruent condition, we merely conclude that the triangle AOB and the triangle the triangle COD. Oh, yeah, I guess I do want to say DOC at the first place. Okay, great. So the triangle AOB and the triangle DOC are congruent to each other, and consequently, we conclude that the corresponding angles AOB and DOC are congruent to each other, since the measure of the arc, the minor arc APB, is precisely the measure of the central angle AOB. And similarly, for the relation between the arc DQC and the central angle DOC, we are done with the proof. Now, as an exercise, you could try to work on the following theorem, the Theorem 2, which is, in fact, the converse of Theorem 1. It says that if two minor arcs are congruent, then so are the corresponding chords. Also, you could try to prove the following theorem, which is going to be quite useful in our subsequent development of the relation between angles and the measure of arcs on a circle over here. The theorem says that if the arc APB and the arc BQC of the same circle sharing only the endpoints B, then the sum of the measure of APB and the measure of BQC is in fact equal to the measure of the arc ABC. So it's going to be the larger arc over here, including both of those two arcs as parts. So the result here is quite intuitive from the figure. We do see that it better be the case, right? Or in other words, we see here that the measure of arcs is additive. So, so this intuitive idea, this intuitive result is going to be quite useful in our development. So as an exercise, you could try to play with it a little bit.